So what is an ocean current and what causes ocean currents? And what's the importance of them? That's what we'll be looking at today. So if you were here, we would have done a lab, and in this lab you would get warm water and you'd pour cold water in it. So the warm water we would have colored red and the cold water we would have colored blue. So once you poured that blue cold water into that hot water, the cold water would have all gathered down at the bottom of the beaker, just like in this picture here. The other part of the lab that we would have done is we would have had fresh water and then we would have had salt water. The fresh water was red and the salt water was green. And so once you mix the two, the fresh would stay on top and the salt would be on the bottom. So in this picture, this would be the hot and this would be the cold down here. So why did this happen? Well, what we learned in Unit 3 is that warm water is less dense. So warm water is less dense, so it goes up, while cold water is more dense, and so it sinks to the bottom. Well, fresh water is also less dense, therefore it floats. Salt water is more dense because it has salt filling in all those gaps, so it's more saturated, making it heavier, and therefore it sinks. Now, this is a key thing to know in order to understand our ocean currents. The density is what's going to drive them, and that's what we'll look at in just a minute. So what are ocean currents? Ocean currents, they're simply when the water's moving from one place to another. Not from waves, but there's just this current of water or this area or mass of water that's constantly going from one area to another. So there's three different kinds of ocean currents: surface currents, deep water currents, and tidal currents. So surface currents are simply the area on the top of the water, the surface, that's moving. This is moving because of winds, specifically global winds. So your surface currents are going to go in the same direction as the global winds. Now, if you remember from Unit 3, we said global winds are curved because of the Coriolis effect. Remember, the Coriolis effect is the curving of global winds that's caused by the rotation of the Earth. And the direction that your global winds curve in the northern hemisphere is to the right. Because if I say, hey, do you live in the northern hemisphere? You'd say, that's right, I do. Therefore, those winds go to the right. Well, therefore, also the ocean currents curve to the right. In the southern hemisphere, our ocean currents curve to the left. So they are driven by those global winds. Surface currents are going to influence the temperature of areas. Now, the main example that we see of this is using the Gulf Stream. The Gulf of Mexico is a body of water right off of Mexico that's very warm. Now, this body of water has a current that we call the Gulf Stream, and that warm water goes up past the U.S. towards Europe. Now, because the water in the Gulf Stream is warm, as it moves by different areas such as the East Coast and Europe, it makes the air above it warm, causing those areas to be warmer. So Europe is typically a cooler area. But because the Gulf Stream is going past it, it warms that area by about 10 degrees. So Europe is 5 to 10 degrees warmer simply because this warm ocean current passes by it. So warm ocean currents that pass by an area make that area warmer. If it's a cold ocean current, then if it passed by an area, it would make that area colder. So the Gulf Stream is known as the heater or the heat pump of the Earth, and it does influence climates by making it warmer as it passes by. So that's the main example of a surface current that they talk about a lot with your North Carolina testing. Upwelling is something else that is created because of your global winds and surface currents. So upwelling is basically when you have wind that moves the top of the water. So if you have a really strong wind, it moves the top of the water away. And as it moves that top layer of the water away, the cold, dense water from underneath comes up to take its place. So this is not a convection current, because in convection, warm water is being forced up. But in this case, the water's not rising because of density. The water's rising because the wind is basically stirring up that water. So the wind blows and moves that top layer away, and that bottom cold, dense water takes its place. And that dense, cold water actually has a ton of nutrients in it. And so upwelling is really important for fishermen because with this dense, nutrient-rich water, fish go crazy. It's like a buffet for them. So if you're a fisherman, you want to find areas of upwelling because it brings in nutrients and it brings fish, and it helps you therefore catch more fish. Now we're going to look at deep ocean currents. That was all talking about your surface water. Deep ocean currents go from the top all the way down to the very bottom of the ocean. And with our deep ocean currents, we call them the conveyor belt. Now, the biggest thing for you to make sure you know is deep ocean currents are driven by density differences. Okay, they are driven by density differences. So what causes deep ocean currents? Density differences. Just like in that picture I showed you at the beginning of the slides, when you mix your cold water with your hot water, cold water sunk to the bottom. Why? Because it's more dense. Now, as that water warms up, it would rise to the surface. And then again, the cold water, it would sink back down to the bottom. So this is just a giant convection cycle created by density differences. The other thing that can cause density differences is the salt content. In that picture I showed you, the really salty water that was colored green sunk to the bottom of the fresh water while the fresh water stayed on top. Now, when you look at the ocean, you have areas of the ocean that are very warm. Those areas are by the equator. The equator is warm year-round because of that direct sunlight. So that direct sunlight causes that ocean water to be very warm. So all that warm water is going to rise to the surface and travel amongst the surface of the ocean. Once that water gets to the poles, it becomes very cold and it starts to sink because it's more dense. And so you have these convection currents going from the equator to the poles. But again, it's driven by density differences because warm water is less dense, cold water is more dense. The other thing that affects the density differences is the salt. All ocean water is salty. However, not all ocean water has the same amount of salt. Some ocean water has more salt than others. For example, when you go to the poles, you have ice caps and glaciers. The ice caps are fresh water, yet they are in salty ocean water. If you've ever wondered why, it's because when the water freezes, it does not bring the salt with it. So at the poles, you have really, really cold, dense water it's extra salty because as all these ice caps freeze and form, it leaves the salt behind. So your polar water is extremely dense because it's very, very salty and it's very, very cold. And so that polar water sinks with great force, which then drives the equator water to move up and take its place. And so that is kind of what drives this conveyor belt. We call these circulations thermohaline circulations. Thermo is referring to the temperature differences created by, or the density differences created by temperature. Haline refers to salt. This is talking about the density differences created by salt. So together, the density differences in the ocean from your temperature and your salt is what causes deep ocean currents. And deep ocean currents are very important to climate because as that ocean current passes by an area, it makes that area either warmer or colder. So if you are where I just put a star, which is more like a circle now, if you live there and this warm ocean current passes by you, then the area is going to become warmer. The climate will become warmer. Now, if you are over here where I put a circle, the ocean current passing by you is a cold current. So the climate is going to become cooler because a cold current is passing by you. So that's how it affects your climates. So the deep ocean currents, they're also called the North American deep water. But again, just deep ocean currents. What's happening is your denser, saltier, colder water sinks and it moves on the bottom of the ocean floor, and your warm, less dense water moves on this top. And it's just exchanging heat. It's making warmth go to cold and cold go to warm. Remember, the earth wants to be balanced, and this is another way of balancing it out. Deep ocean currents are also going to mix up oxygen, which is very good for different animal species. Now, The one problem that we have is that deep ocean currents theoretically could come to a stop, and this would be a very big deal. Okay, when you have global warming and the earth gets warmer, when all of those ice caps melt, that is fresh water being returned to the salt water. Because you're melting all this fresh water in, it is making the water more diluted and less salty, therefore less dense. That water is also now warmer and therefore less dense. And if you don't have super dense, cold, salty water sinking at the poles, it can stop your ocean currents altogether, which would then have very big influences on our climate and with our ocean species. Now, this video right here is very good at explaining why global warming it's good at explaining why we have ocean currents, but also why they could stop due to global warming. Now, if you are confused about any of the stuff I've talked about, this video down here that I've made very large is a great resource that just gives you a good visual of how these ocean currents are being created. So again, if you are not sure what on earth I'm talking about, please watch that video for more support. So now we're going to look at our last type of ocean current, which is a tidal current. And really all I have to say about this is when your ocean moves because of tides. So if it's high tide, the water goes up, and if it's low tide, the water goes back. So that's just your ebbing and your flowing of your water back and forth, created by tides. Next, we'll look at tides, and there'll be more detail based on that. Okay, so try to summarize what causes deep ocean currents. How do they affect climate? And then how would global warming affect them? If you can answer those 3 questions without checking your notes, then you have a very good understanding of ocean currents. If you cannot answer these 3 questions, then that means you need to go back and make sure you study this a little bit more. But let's continue on to tides. Tides are created by gravity. So first of all, what is a tide? It's just a changing in the elevation of the ocean water. So in high tide, the ocean is actually becoming deeper. And low tide, the ocean is a little bit more shallow. And we'll get to what causes these tides and why it's becoming deeper or more shallow. But when that ocean water is deeper, that's why it goes further up on the beach, because that water can't just pile up, it's got to move forward. And when the ocean becomes a little more shallow in certain areas, that water moves back away from the shoreline. Now, what causes tides? Gravitational forces of the moon and the sun. This is a big deal for you to know. The moon and the sun together. The moon has a bigger effect on tides. Why? Because the moon is closer. The sun may be much larger and have a stronger gravitational pull, but since the moon is closer to us, it has more of an effect on our tides. Make sure you know that. Also, make sure whenever you take a test, you read your questions. If a test ever says what causes ocean tides, and the answer choice A is the sun, B is the moon, C is, black holes, and D is the moon and the sun, then D is the correct answer. Because if it has both of them, always pick both answers, not just the one. Now, sometimes it may not give you both, but just be sure you always read answer choices carefully and take your time on test. So we have 2 types of tides. One is called a spring tide, and the next is called a neap tide. Let's look at your spring tide first. So when you have a spring tide, let's see, you have the sun in the middle. There's the sun. And then you have the earth that is moving around the sun. So typically, they're going to draw earth in 4 different spots. Now, do we have 4 earths at one time? No, we only have 1 earth. But in the diagram, they're showing you that the earth could be here, the earth could be here, it could be here, or it could be here down at the bottom. So you need to make sure that you don't think of this as 4 different planets. It's just 4 different locations the planet could be. Now, the other thing they're going to draw is the moon. So the moon could be, because remember the moon is going around the earth. So it could be between the earth and the sun on this side, or it could be on the other side of the earth. So you could have the moon in those two locations, or the moon could be above and below the earth. So it could be on the sides here, or it could be up and down. When we are looking at our spring tide, and I'm going to have to actually redraw this real quick. Sorry about that. When we're looking at our spring tide, again, you have the sun, and then we have our earth. 1, 2, 3, 4. Spring tides have the moon that's in line with the earth and the sun. So it's in a straight line. So it could be here or it could be here. When the gravitational force of the sun, moon, and earth are all added up together, you have a spring tide. This makes extremely high tides and extremely low tides. When you have a big difference in your high and low tides, that's what we call a high tidal range. Range is the difference in a set of numbers, so this just means it's very, very high, and then the very, very low tide. So again, this is like you're adding sun plus moon plus the earth equals a spring tide. Now, I can remember that a spring tide is in a straight line because spring starts with an S, and this is in a straight line all together. So spring tide is when the sun, moon, and earth all form a straight line, whether that's going sideways or whether that's going up and down. If they form a straight line, it is a spring tide, and they will have extremely high tides and extremely low tides. The next type of tide we have is called a neap tide. Now, the way that I remember neap tide is neap sounds like leap, and leap starts with an L. So this is when the sun, moon, and earth are going to make an L shape. So again, you have the sun. So we'll draw that. And then it's going to show you the 4 different locations that the earth could be. It could be here, could be here, here, or here. What's different now is where we have the location of the moon. Instead of the sun, moon, and earth being in a straight line, they're going to make an L shape. So the moon would be here or it would be here. And so that would make an L, going like that. That's an L. Neap sounds like leap, so it makes an L shape. So if the moon is here or the moon is below, and it's making that L shape, now your gravitational forces are offset. They're not pulling together. If the sun and moon are pulling on the earth at the same time, that's going to cause really, really high tides and really, really low tides. If the sun is pulling in one direction this way and the moon is pulling this way, they're pulling in 2 different directions. Therefore, your high tide won't be as high and your low tide won't be as low. So there will be a smaller tidal range, and those tides just won't be as drastically different. This picture is simply showing you the difference in your extreme high spring tides and your lower neap tide. So in the spring tide here, you can see the high tide is a lot higher than it is on the neap tide, and your low tide is much lower than it is on the neap tide. So this has a bigger difference in tides when this has a smaller difference. So that's just showing you what we mean by extreme highs and lows in your not your smaller tidal range. So this is another way that you could see the diagram for your spring tides. Again, spring tide is going to be making that straight line between the moon, earth, and sun. And your neap tide is making that L shape, okay, because they are offset. Now the next thing I'm going to explain, and the last thing with tides, is where you have your high and low tides. It's what we call a tidal bulge. Okay, here we have the diagram of what a spring tide would look like. And I know this is a spring tide because the earth, moon, and sun are all in a straight line. Now remember, we do not actually have 2 moons. This is not moon 1 and moon 2. This is just showing you the 2 different places that the moon could be to create this. So let's go ahead and take a look. Now, when you have your sun and moon added, the forces are added together, they are both pulling the water because the water is fluid on the earth, so it's pulling the oceans towards it. That makes it bulge out, making the ocean a little bit deeper, and this is called a high tide. Now, when you have the moon over there pulling the ocean water towards it more like that, it's going to pull the water really far that way, but it's going to pull the earth just a little bit in that direction. And when it does that, it leaves this ocean water alone, doesn't move it at all, and that creates another high tide bulge on that side. Now, because the ocean is now stretched out, just like if you got a rubber band and pulled it out, it's got two high tidal bulges there, and then it has low tide over here because it's pulled thin. So the moon and sun are pulling the ocean water really far in one direction, creating a high tide bulge. It moves the earth just a little bit, leaving another high tide bulge on over here, because the sun and moon are not going to affect the water on that side of the earth. So the two high tide bulges are on both sides in line with the moon, and your low tides are on the opposite sides. So that is going to be what we call a spring tide. Now, when we have a neap tide, I'll go ahead and erase this. When we have a neap tide, our earth, moon, and sun are not in a straight line. Remember, they're making an L shape. So let's erase my moon. The moon is going to instead be over here. And the moon is going to, because remember, the moon has a greater effect on high tide than the sun. It's going to pull that ocean water towards it, creating a high tide bulge. On the opposite side of the moon, it's going to pull that water really far, and then it's going to pull the earth just a little bit that way. It doesn't pull anything on this side, so this water's left behind, and that's another high tide. Then the low tide is on the sides where the sun is. High tide is always in line with the moon. Low tide is going to be the opposite sides of where the moon is. Now, this is a difficult concept to understand, especially with me drawing pictures, because I can't show you how things are moving. If you were in the classroom, I would have strings where you could manipulate this and see it for yourself. If you don't understand what I was saying, which you probably don't, there's no shame in it, there is a video with a visual that I beg you to please watch. If you do not get what I was saying, please watch the spring and neap tide video. It gives you, they actually have a string and something that's showing you why the high tides are where they are and why the low tides are where you are. And then this picture is just showing you the difference in the high and low tide when you have a spring tide. So please watch this video if you don't understand. That is it for this video. That's all for your ocean currents and your tides. Please watch these videos if you're confused, and then if you're still confused, please email me or contact me to let me know. And that is it for this video.